know, some of you guys actually got questioned about the proof exercise I distribute on the webpage. I'm going to do that maybe the last point for today. That will take some time. Apart from that, you can ask any others. Yes? Subcontracting.
Yeah, so is that the invariant is same with the postcondition, right? So the loop invariant in the for example, I have two classes and B inheritance from A. So and they both have loop invariant. So is that the loop invariant?
I see what you mean. Yeah. So the answer is no. Okay. You're basically talking about this scenario here. Let's say you have class A. Let's say it is effective, and also you have a subclass called B. Okay. Let's say we have, find max, for example. Okay. Find max, and also typically you shouldn't show any implementation in the bound diagram, but let me just show it just for the purpose of illustration. If I say do over here, okay, I can have the from until. After from, you should get invariance. Let me set up the context first. Okay, let me write it more properly. Okay, invariant, let's say some Boolean expression I, and then the rest. And then for this particular find max, you have some postcondition, let's say R. Okay? So we got two Boolean expressions over here to worry about. So you got your invariance, and also you got your postcondition, right? So now let's worry about a subclass. Let's say for this subclass here, it's also effective. Let's say we want to redefine the find max, let's say. If somehow you say find max over here, and you say do, let's say over here for find max, you're using a different algorithm to actually calculate the max. Let's not worry about exactly what it is. Somehow you also got from, and also you got invariance. Okay? Let's say in the previous one, let's call this I1, R1. Okay? And here, let's say I2, and also after this, you got ensure, then, right? That's for subcontracting. And then we got R2. Okay, so now let's say I2 and R2 over here. Okay, so now we got four Boolean expressions over here to worry about. So as we learned from the subcontracting lecture, what should be the relationship between R1 and R2? Let's talk about R1 and R2 first. If you want to judge to see if the design is correct or not, what should you prove? R1. Okay. Okay, let's see. If you say R1 and R2, so this is something that will be checked at the runtime. It's not really for you to judge whether the postcondition you have is effective or not, right? It's appropriate or not. So this is the runtime checks. This is the runtime checks. However, if you want to see to judge if your design is correct or not, what should you do? Okay, anyone? What should we prove? Yep, exactly. You want to make sure ensure no less than the superclass contract. Yes, R2 implies R1. Okay, just a very quick review. Of course, you got also the rule for the precondition, right? Okay, so now the question really was, what about I1 versus I2? We shouldn't have any constraint on the relationship between I1 and I2. Intuitively, you can see this loop here is part of the implementation, which is hidden, right? And also, this loop over here is also just another implementation. So from the external client's point of view, they don't care what algorithm you're using. So looping variant is only for you to prove your internal implementation is correct. So they are not really visible, right, in this case. So now, for I1 and I2, they don't have any relationship. Well, thinking this way, thinking another angle, you can think about the I1 you have over here might be very specific to how exactly you're trying to implement using this particular loop. On the other hand, I2 here is also very specific to how you do it for this particular implementation. So they have nothing to do with each other. Okay. Doesn't matter. Well, I shouldn't say doesn't matter. Of course, the invariant you have should be very specific to how you want to prove the correctness for your implementation for that particular loop. It depends on the coding. But for the postcondition and precondition, they're part of the contract view. They're public, so you have to worry. Yeah, makes sense? Yeah.
There is something that you should know about is the relationship between I1 and R1. What's the relationship between I1 and R1? Or I2 and R1?
Yeah, anyone? Let's say I1 and R1. So what kind of conditions do we have? Let's say. Remember we got this, let's say the proof obligation for partial correctness, right? Let's take one, yeah, go ahead. Okay, I'll just write exactly what you say. Okay, let's say until over here, let's say B, okay? And B, that means we're exiting, we're terminating, okay? Yep. That's one of them. R1, yes. Yeah. So that means upon the termination, you should really establish the postcondition. Of course, you also got the another two about if you can maintain the invariance or if you can establish the invariance, right? You got other two as well. Yeah, you're going to establish and maintain, yes, correct, yeah. So after the from part, which will be executed only once, you want to establish the invariance. But between each iteration, you want to maintain the invariance. Oops, sorry, yeah, go ahead. What about is a class invariance, okay? Yeah, it will come back, sorry, I should keep in mind not to cross this over. Let me just bring it back, sorry. Okay, the question was really about class invariance. Okay, let's bring this back first. Okay, good. So for class invariance, first of all, what's really class invariance? Number one, class invariance is for you to define how each object is valid for that particular class, right? If you got bank account class, the invariance should be, maybe the balance should be positive, should not be negative, right? So now if you talk about subcontracting, right? So as we said before, let's say you got, again, let's draw a similar diagram over here. Again, we got class A, and also we got a subclass over here, B. Let's say here we got invariance. Let's say, I would say I1. Invariance, let's say I2. Okay, so what should be a relationship? You tell me. Which one should be stronger than? I2 implies I1, yeah. Okay, so now I2 implies I1 should be something you want to prove to be the case. And so this is what you want to prove. At the runtime, what's going to happen is you're going to accumulate the invariance, right? So whether you want to check some instance for of type B, you're going to check that I1 and also I2. Okay, so there are two different parts. One is about statically how you can prove the invariance appropriate between the two classes. And number two, at the runtime, how do you do the runtime assertion monitoring for the invariance? So the two parts over here, right? And one more thing to say. The way we actually judge the appropriateness for the class invariance is pretty much like how we do it for postcondition, right? You can see here we got R2 implies R1. That's simply because you can think about class invariance as a postcondition for every feature, right? As we said, right? So the rule is really the same. Proof, you have to apply the logic learned back in 1019 or 1090, right, to prove. I'll give you one example, very easy. Okay, let's say, how about this? Proof, I'll give you two examples. Let's say example number one. Let's say we have some attribute x of type integer, okay, in class A. So you will be inherited to class B as well. If I got x larger than 0, okay? So that means under no circumstances for the lifetime of any object of type A, should you get x less than or equal to 0. It should always be strictly positive, right? Let's say over here we got x larger than or equal to 0. So now, let's say this is what's given to you in the exam, for example, right? So how do you judge whether the current invariant is appropriate or not? Is it appropriate? Okay, so now, why is not appropriate? Exactly. Okay, that's good. Okay, so now this is what you want to. So either you prove or disapprove. If you want to disapprove a predicate is not the case, you give counterexample. So now what we want to prove is something like this. The I2, which is x larger than or equal to 0, implies I1, which is x larger than 0. It is not the case, right? So this is not the case. You can give one counterexample. You can say when x is equal to 0. Because when x is equal to 0, 0 larger than or equal to 0 will be true, right? 0 larger than 0 will be false. And you know the truth table for the implication, that will be just false, right? Yeah. Yeah, I would say here you just have to give the counterexample. Once you give the counterexample, you can briefly just say, if I plug in the number for x in this case, it's going to give me false. So it cannot be proved.
So we don't have to necessarily give them.
You don't necessarily have to, but the counterexample must be clear enough if you want to disprove. Of course, if you want to prove it, you have to be more rigorous over there, right?
Let's say this was the exact question on example. We would say the relationship between the first one and the second one would be implication. So I2 would I1.
Yeah, so this is what you have to say. If this is exactly what you're given, and the question is, justify, let's say this is a question. Let's say this is exactly what you're given. You're given this class, this attributes, the two invariants over here, okay? The question is, justify whether or not the class invariants in A and B are appropriate. You know, something like that. So now you want to justify, right? So now, first of all, you want to identify whether or not it's appropriate or not. You would say it is not appropriate because when we try to prove this particular predicate here, which is the rule for judging if invariant in the subcontracting context is appropriate or not, right? This one here does not hold in general. And because, for example, this scenario here, you don't want to give one counterexample. Yeah. Yeah. Mm-hmm. 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 So this is something you got to prove, just prove statically. So now at the runtime, if at the runtime, so what you will check, let's say this. If I got B of type B, right? If I say creates B, something like that, okay? So now what's going to be checked exactly to make sure this initial instance can, let's say, B.make. And of course, you might have some make feature over here, let's say, right? So now, after we have created this particular instance of type B, what exactly will be the invariant being checked, right? So what you will check would be, you will actually accumulate these two using conjunction, right? So what you will get is x larger than, I'll put it here. So at the runtime, you're going to check to see x larger than 0, which is here, conjoined with x larger than or equal to 0, right? In this case, because this guy here is stronger than this, right? In that case, it would just be equivalent to the stronger guy. Okay, that's being checked. Yeah. But when you have class invariant in a subclass, it should be stronger, right? It should be. So two issues here. One is about how you prove, and the other one is about what's being checked at the runtime. Okay, any other question about this example here? Yes, go ahead. Yes.
Oh, so if you actually put in a weaker like invariant, I guess, in like a descendant of that type, or a child?
In this case, yes, we are indeed putting a weaker invariant.
So it's just like essentially isn't doing it.
Yeah, exactly. That's why, logically speaking, it's not appropriate. Because whatever you put as a weaker one, it will be somehow dominated by the stronger one in the superclass anyway, right? For another example, for some contracting, you can refer to the slides where we talk about, remember the polygon, also rectangle, right? There's also another example you can see about invariance. Yeah, you can also see. Any other questions about subcontracting? Yes. Yep. Okay, first of all, if we got multiple inheritance, let me just say this. Let's say conceptually you want to have, let's say, multiple inheritance like this, right? Let us see the descendants of A and B, okay? Let me just set out the context first. Let's say feature, so we talk about invariance, or you want to talk about invariance or postcondition? It should be similar. Invariant first, okay? Let's talk about invariant first, and then we'll talk about feature. If you say invariance I1, and also here, if you say invariance I2, okay? Basically, in that case, you're going to accumulate both I1 and I2, okay? So now, if I got another invariance over here, so now let's say I3, okay? So now, what should we prove to make sure they are appropriate? Yeah. Yeah, exactly, because they will both be accumulated. I1 and I2, right, will both be accumulated. They should be no stronger, okay, sorry. Should be this way here. I3, which is a subclass, that should imply this one here. Well, you can think about basically I1 and I2, they will both be accumulated to C. But now you want to make sure the one you put in the subclass is a stronger one, right? That's exactly what we're proving here. So I3 should be implying I1 and I2. Okay? Okay? That's number one. Okay? That's about invariance. Okay? Let's talk about feature here. The feature is more interesting. Okay? So now let's say we got, let's say feature F, and then let's say we got ensure, let's say R1. Okay? And also we got the same name, right, as you said, right? And also we got ensure R2. Okay? So now first of all, if you simply put something like this and then without doing any renaming, it's not going to compile. Because now you can see you're inheriting one feature called F into here. You inherit another one with the identical name over here. You got some name clash. So you have to do some renaming first. Okay? So now let's say you do the renaming. Okay? Let's say over here, you can look up the exact syntax. I'm going to write it here. Okay? You can say class C inherits A, and also we're going to rename F as, let's say F1. How about FA? Okay, there's an F from A. And also you can say also inherits B, rename F as FB. So now in C over here we got FA and FB. Okay? So now if you want to further define the contracts over here, oh sorry, that's too big. Let me just fix this quickly. So now let me write a little bit more. Okay, so now over here in the C, let's say we try to also redefine FA, just for example, right? So now if you say FA, ensure, and then let's say we got R3. Okay, so now what should we prove in order to judge R3 over here is appropriate? Yeah, that's exactly right, because you can see that according to the renaming clause over here, FA is in relation to F in this particular class over here, right? So that means you have to relate these two predicates over here. So R3 implies R1. Your code wouldn't compile without renaming, so you have to rename. Okay, so you can now relate the features more properly. Okay? Okay, any other questions about subcontracting? Yes. The feature name is, no, the feature name is F. Yeah, the feature name over here, you can see F, and then we rename to FA and FB, right? You can see F and F, they will clash in the subclass over there. You cannot have F and F, right? So that's why I renamed that to FA and FB. Okay? Yeah, and then R1 over here is a post condition. Huh? Did I say feature R1? Oh, I see. Ensure, oh, what does ensure, right? So which part? You mean ensure, right? Ensure R1. Feature, okay, maybe I simply said it wrong. Okay, anyway, so we got feature F. Okay, feature F has the post condition R1. R1 is a Boolean condition, right? And F is renamed to be FA over here. And also we got another feature F in class B. And also we got a post condition R2. And it is renamed to be FB in class B, right? Okay. In class C, yeah. Yes.
Just to clarify, so R3, like the post condition for C, would be stronger than
R1. Yeah. Yeah. So R3 here has nothing to do with R2, because R3 is actually associated with FA, which according to the rename clause is associated with F in A. Okay. Good. Yeah. So this is something that we didn't really say explicitly in the lecture, but based on what you learned about renaming, based on what you learned about subcontracting, that's something you are expected to judge, right? Yes.
Just want to clarify, I think I know the answer, but suppose you have a parent and a child.
Okay.
And the child has a stronger invariant.
Mm-hmm.
I instantiate an object of the parent, and I satisfy its invariant, and then I cast it as a child, but it doesn't satisfy the child's invariant. Would that cause a runtime error? I assume.
Okay. Okay, I see what you mean. So I would say it depends on the dynamic type of the objects. Okay, let's see this. I see what you mean. Let me set it up. Again, let's use A and B, just easy. Class A, and also we got class B. Of course, you're encouraged to try this out also in Eiffel Studio, right? Just make sure we are okay with that. Let's say again we got X attributes of type integer. Okay, let's say we just got, let's say we have the make feature. Okay, so now we have an X value and then of type integer. I'll say int just for short. And then, well, again, you shouldn't show code in the, let's say ensure after this, X is equal to AX. Okay, so now let's do some invariance over here. So I can say invariance. Let's say X is larger than or equal to 0. Okay? And now, let's say for B, we just have a stronger invariance over here. Okay, let's say X larger than 0. Okay? Let's say, as far as the proof is concerned, we're okay, because X larger than 0 does imply X larger than or equal to 0. So let's talk about this. Now, if I have, let's say, let's talk about a simple case first, okay? If I have B of type B, okay? So now, if I say creates B dot make, let's say if I simply do 0, what's going to happen? What kind of error? If you believe there's an error. Why would there be a compilation? Well, of course, you got to say local, right? And local and do. Let's not worry about that kind of stuff over here. So let's say we declare B to be of type B, okay? And then we're trying to create an instance of type B. So that dynamic type should be B, right? So now we're trying to pass the initial value to be 0. So now, question is, what exactly will be the invariant being checked in this case? Well, or just what we just said before, there'll be some runtime rule to follow, right? So in this case, at the runtime, right, what will be checked will be whatever that's in the parent class, X larger than or equal to 0, and also X larger than 0, right? We know that this guy here is stronger. So this is simply just equivalent to X larger than 0. Because the So what's really important is about the dynamic type in this case, right? It's going to check that. Okay. So now it will simply say, well, of course, in this case, you're going to get class invariance violation. Okay. Yes, questions first. No. For the precondition, it's or. For the precondition, you want to check at the runtime. Yeah, don't get confused. So for postcondition and also class invariant, when you check at the runtime, it should be conjunction. Right? Yeah. Okay, so now let's try this. Let's try another one here. Runtime error. It's not compile time error. Compiler cannot do any proof for you. Okay? So compiler can only do some runtime check. That's why we kept saying. So compiler, okay, if you talk about compiler, what a compiler or the runtime machine, the runtime assertion monitor. Okay, what they will do is going to check at the runtime that x larger than or equal to 0 conjoined with x larger than 0. This is something they will do for you. They don't really do any proof for you. Yeah, proof is hard to do by the compiler. Okay. Okay, you say ax greater than or equal to 0. The precondition require y. What? You mean, say it again. What rule? But we didn't have that. Mean subcontracting rule or? Well, you can turn this into a whole triple. How about that? Right? So if you want to do any, you want to formulate a correctness predicate for this particular constructor, you can do a whole triple. So how do I do a whole triple? Basically, at the moment, since we don't have any precondition, right? So that means it's simply just true at the moment. Okay, let's say the implementation over here, we simply say, let's say x is assigned to ax. Okay, and we want to make sure the postcondition is such that we want to make sure invariance is also satisfied, right? Okay, so you want to make sure x is equal to ax, which is what we got before. But now we want to make sure the invariance is also established, class invariance. Okay, so now if you are given this particular whole triple over here, okay, precondition and also postcondition and also class invariance. Okay, so now is this whole triple can it be proved as true at the moment? How did you figure? What should you do first? Let's say we give you this particular whole triple. We ask you whether or not this whole triple can be proved true. Okay, how would you prove it? You want to find some counterexample, right? But before you can find a counterexample, right, you want to calculate something. Weakest precondition, yes. You want to help me out to formulate it? So I want to first of all, I want to calculate the WP, right? Of what? Okay. Exactly what's here, right? Okay, I'll write it down. And then x is equal ax and x larger than or equal to 0. Okay, let's say we calculate that. And then what? You want to make sure Yeah, exactly. Well, that's exactly what we said in the class, right? Okay. And of course, you can easily do the weakest precondition calculation here by using the assignment rule, right? I can let you do a substitution, right? Once you do it, you can see what it is. What would that be, by the way? That should be an easy way to do. Easy thing. So what will be the WT here? Okay, so now you want to substitute every free occurrence of x by ax, right? Over here and over here. So ax equals ax and also ax larger than or equal to 0. How do we simplify? Right, this is true, right? And also by the identity of a conjunction, you know, true and something will just be something, right? So just equivalent to, of course, you want to justify in more detail in the exam. Make sure it's clearly written out. So WAX larger than or equal to 0. So this predicate here is the weakest precondition. So now we're asking whether true implies this. Does it? If no, give me one counter example. -1, right? Exactly. Yeah. Okay, let's say, so true implies AX larger than or equal to 0. It's not the case, so you can say counter example. AX, for example, if you just give a negative value. In that case, right, you got true implies false again. Right? Okay. Are we okay with this? Well, we just did one exercise, right, for WP, right? Yeah. Yeah. Mm-hmm. Yeah. 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 So basically, yep. Mm-hmm.
So what I was pointing out is that we're going to have trouble with B now, because the precondition, what's going to be the precondition in A? B? We're going to have to strengthen the precondition with x greater than 0 to ensure the invariance. But now we're requiring more of the x. That's the problem that I was pointing out, which led to this very great example. It's no really good stuff.
Yeah. So now let's say you got make feature over here, right? So now let's say over here. First of all, let's say we got true over here, right? Let's say we got true. Okay, let's say this. Let's say we fix this a little bit. Okay. So based on what we just proved, what we try to justify, let's say over here for the make, okay, I'll put it here. For the make, I'm going to say require. We know that the weakest precondition should be this. So I'll put A, X larger than or equal to 0. Okay, let's fix that. So now, let's go for this particular one over here. Let's say make. Let's talk about, we redefine the make. Okay, somehow. So now let's talk about the contract. So it's going to be require else. And we know that in this case, the invariant is actually stronger. Agree? So now, what should be the weakest precondition for us to establish x larger than 0? Huh?
So I know which is stronger than x greater than 0, but since runtime is at all, so you cannot really stronger it.
You cannot really strengthen it, right? Okay, let me just make sure that point is clear. Okay. So we can easily calculate what is the weakest precondition for in the implementation to establish the invariant, right? In that case, we do the similar exercise here. That would just be AX strictly larger than 0. Okay? But now, what's the problem here if we put AX larger than 0? It's stronger, right? It should be weaker, right, in this case. So that means at the runtime, what's going to happen? So now at the runtime, okay, so now let's say, let me highlight quickly. So now we have, first of all, AX larger than or equal to 0. And here we got AX larger than 0, right? We got the two preconditions here, okay? At the runtime, what we're going to have is this, okay? So at the runtime, you're going to check basically AX larger than or equal to 0 or AX larger than 0. Okay, what's that equivalent to? Greater than or equal to 0, yeah? Because the weaker one, right? If you do conjunction, it should be equivalent to the stronger one. If you do disjunction, it will be the weaker one, right? That's equivalent to AX larger than or equal to 0, right? That means you still run into that trouble, right?
You should have made this an exam question.
Too late.
Maybe we can still do so.
Shall we? Yeah, we could add an extra page tomorrow.
It could be a stage that people who can't get.
Yeah, it could be. Again, there are two things you gotta watch for. One is about proof, statically on the paper, and also the compiler doesn't do the proof for you. You only worry about what's going to be checked at the runtime. Right?
This is all to ensure the risk of substitution principle is used. The only way to make subcontracting work, the only way to do it. Otherwise, inheritance is not going to work out.
Yes. Any assignments and substitution? Okay. They belong to different categories of concept over here, if I understood you correctly. Okay. Let's say you got WP. Let's say we got X. Let me give you the simplest example. Okay. It's assigned to, let's say 23. Okay. And then let's say the post condition we have is X should be strictly larger than, let's say 22, for example, right? So now, according to the, well, this, of course, that's how you can calculate, right? You're going to justify in the middle. You can say WP rule for assignments. Okay, let's just write it out, okay, just for your information. The rule simply says the following. If you got WP, X is assigned to any arbitrary expression. In this case, it's simply just 23. Okay, and here you got some R, which is a post condition, any Boolean expression, right? According to the rule, it's going to be just the same as R, except that every free occurrence of X will be substituted by E. Okay, so here we talk about, when we talk about substitution, it's not really variable assignments. Variable assignment is more like a programming concept. When you say substitution, you're just doing some replacement over here in the Boolean predicates, right? It's different. Okay. Yeah, you would just say X is simply substituted by E. Okay. So now, just to clarify, over here, this is more like a programming assignments. Okay, so this is more about substitution of free occurrence of X. Yeah, they're different. Right? Yeah, one takes place in like a programming context, right? You're trying to write code. You just say assignments, which means I go to some memory location and modify what's stored over there. But when you say substitution, it's more like a mathematical notation, right? You got some Boolean predicates. You want to replace every free occurrence of certain variable by some value because you do the assignments. Okay. Any more questions about subcontracting? You can feel free to ask other questions. You know, it doesn't have to be subcontracting or WP. Yes.
Do you mind doing WP stuff for the whole everything? I want to make sure, like, I have trouble with concrete stuff, so I'm not sure how to conclude it formally, but just like,
You want to do one example, right? Okay. This one here? Okay, how about this? Okay, let's say we consider the following code. Let me try to do that first. Let's say max of. Let's say we got X, we got Y of type integer. And then it's going to return an integer. Okay? So now, let's say require and also ensure. Let's say require simply X and Y. Let's say X and Y are both positive, let's say. Okay. Okay, and also let's say do body here. You want the if statements. Let's say if x is strictly larger than y. Oh, you know what? Let's say this. Let's make it a little bit easier. Let's say x is simply not equal to y. Okay, like that. Okay, just make it easier so you don't have equal values. In which case you can return anything, right? You can return either value. They're the same. Okay, if they're strictly larger than, and then you would say result is assigned to x. Otherwise, result is assigned to y. Now, what would be the post condition here? Well, since you suggested the question, right, why don't you come up with one post condition? We will see if we can prove it. What should be the post condition? Okay, good. You're saying result is greater than or equal to x conjunction, right? Okay, sure. Okay, good. Let's say we have this. Okay, let me just put. So this is the question you're given, something like that. So now what the question really is. Prove or disapprove? Okay, here we just say max off. Okay, that's a question. So now, how do we do it? Okay. Well, if you want to prove it, you want to use a Hoare triple, right? So the first step, you want to formulate a program using a Hoare triple. Agree? Okay. So now, step number one. So step number one, you want to formulation. Formulate a program into a Hoare triple. So now what should I put? Curly brackets, right? The syntax got to be right. Okay? What should I put inside a curly bracket here? X not equal to y. Okay, good. All right. And then this would be the programming text. Let me do a little bit of to make. You can feel free to do this in the exam. That's also fine. Let's say this is S1. Okay. Let's say this is S2. So I would say if x larger than y, then S1. Otherwise, S2. Okay. And then the post condition would be this and this. Okay. Result larger than or equal to x, and I would say R for the result. How about that? Result larger than or equal to x, and result larger than or equal to y. Okay, that's the first step. Formulate the Hoare triple first, in case we don't give that to you. Okay, formulate first. And now, what would be the second step? Yeah, I want to do a WP, right? First of all, we calculate the WP in order for the orange to establish the blue over here. And then you want to see if this original precondition here implies the WP. Okay, let's do that. So now calculate the WP. Okay, so now we can say, okay, let's do that properly. Okay, you will calculate the WP for if x larger than y, and then let me write it out. R is assigned to x, otherwise R is assigned to y. Okay, I'll just omit the and keyword over here just to save some space. And then it's going to establish R is larger than or equal to x, and R larger than or equal to y. Okay, at the moment we don't worry about this just yet. You'll come back in step 3. Okay, so now what should we apply? What's the rule to use? Should we use the rule for assignments, alternation, or sequential composition? Alternation, right? Okay, you can see the overall structure is really if then else. Okay, so now we should say WP rule. So this justification step is very important, right? WP rule for alternation. Okay, so now what should that be? Well, yeah. X greater than Y implies, yes. Implies what?
Implies the R and R equal to X. Like the postcondition and
Yeah, let's do one step at a time, right? Basically, you got two branches. Either you can go for this branch, right? If you go for this branch, that means the antecedent over here is true, right? If you go for that branch, you must make sure we satisfy the weakest precondition for this branch to establish the postcondition over here. Agree? Okay. So it's going to be the WP for R is assigned to X to establish R larger than or equal to X and R larger than or equal to Y. Okay, let's move this over. Okay, are we okay with the first branch? Okay, so now, of course, let's put in the second branch as well. So now, what should be the antecedent in this case? Yeah, exactly, the negation of that, right? Well, you can simply not the case, X larger than Y implies, so now also the WP for, now we talk about second branch over here, right? Okay. R is assigned to Y to establish this guy here, the common postcondition, right? You want to make sure both branches can establish that. Larger than or equal to X and R larger than or equal to Y. So now, how do we put these things together? Conjunction, right? Remember in the lecture we talked about why disjunction wouldn't work, right? Make sure you understand that, okay? You want to make sure either branch 1 or branch 2, both of them should be able to establish the weakest precondition. Okay, so now what would be the next rule to apply? For assignment, right? You can see what's left. One single assignment and another assignments, okay? So now what we can say is equal to WP for assignments, let's say twice. Okay, for this guy here, every occurrence of R will be replaced by X. X and X over here, right? So what we get is X larger than Y implies, and then we got X larger than or equal to X and X larger than or equal to Y. Okay, so now I need some more space. What I can do is like this. Oops. Let me continue to the next page. That would be easier. How about that? Okay, let me continue from the next page. Okay, so now let me write it out quickly. Okay, that will be X larger than Y implies, and over here, X larger than or equal to X, and also X larger than or equal to Y. Okay, we'll do simplification in the last step. Okay, so now, what about the second one over here? Well, antecedent will just be the same, right? Just the same as what we wrote over here. Okay, so that would be X less than or equal to Y, right? Implies. So now, what should this part be? Yeah, exactly. Every occurrence of R will be replaced by Y. Okay, Y larger than or equal to X, and also Y is larger than or equal to Y. Okay, so now we can say some simplification. How about this? Let's be more complete. This would be true. This would be also true, right? X larger than or equal to X is equivalent to true. Y larger than Y is equivalent to true. Okay? And also, true and P is simply just equivalent to P. Right? What you learned before. Okay, let's do one step at a time. So that means this is simply X larger than Y implies, so now this is why we can simplify that out, right? That would just be X larger than or equal to y. And x less than or equal to y implies y larger than or equal to x. Okay, so far so good? So now, are we done? Well, how do you go further? Why is that? Well, does this implication hold? Yes? No? Well, think about it informally, okay? Let's say if x is strictly larger than y, right? Yeah, it should be true, right? Yeah, let's say if 4 is strictly larger than 3, right? And 4 larger than or equal to 3, would that be true? True, but if you flip the order, it wouldn't be the case, right? Agree? Okay. So now you can simply say some arithmetic. Okay, so here this part would just be true. Okay, let me just say one more thing. So if you apply the arithmetic, so this part will be true, this part will also be true. True and true will be true. Yep. Over here. Okay, yeah. Okay, so now what we have is true and true, right? So just get true. So what does that mean? Yeah, so basically what's true over here, first of all? What's the true over here? Yes, don't lose the big picture, because remember we started with step 2, right? So true here is the weakest precondition for this whole program over here to establish the postcondition, right? Okay, I'll just say the program you have to establish R. That's what you should have in your mind. Okay, so now, are we done? To answer the question, yeah. Do you think we're done? Well, so far we completed 2 steps, right? We formulate and also we calculate. Anything else we want to do? Yeah, you want to do some proof, right? You want to make sure this original precondition you had in your program implies they're true, which is the weakest precondition, right? So now, the final step over here, it will be number 3. So you want to prove, in this case, right? You have over here, x not equal to y implies true. Well, that's trivial, because anything implies true, okay? Okay, so now you can make the conclusion, so the program is correct. Okay, so that's a complete example. Yeah. Well, of course, if we only, okay, if we only give to you just the program text and ask you whether or not it is correct, in that case, you will have to do all the 3 steps. It could be that we give you maybe the whole triple. In that case, you don't have to do the formulation. Right?
Can I point out something?
Yeah, of course. Go ahead.
You should make the connection between the WP and the Moore calculus.
Jonathan, you want to write on the iPad? Or?
I don't know if I can.
Okay.
do it.
Okay.
So we have, I'm just going to do it on the board.
Yeah.
Okay? So we have require. And then in the body we have if x is greater than y. I'll just say r. Right?
Yeah.
X else. R is y. So what we really have to prove, if we were using Bohr calculus and not the WP calculus, what would that be? So I'm going to just put this in a box. That's the code, right? I'm going to put this in a box. And what I want to do is, whatever is in the box, I want to write out the precondition, let's call it Q, and the postcondition, let's call it R. So question, what would the Q be over here, the precondition? Question mark, right? And the postcondition, firstly, we know that if you're going over here, x is greater than y, right? The truth is, we also have x is not equal to y.
Oh, yeah. So,
Right, so we don't need it in this calculation. It actually was not needed, right? But truly, what we have is x not equal to y, because we have that precondition, and x is greater than y. And what do we want to have true over here? We'd like to see that postcondition true. So we'd like to see that r is greater than x and r is greater than or equal to y. Let's do this one over here. Same thing, right? We're going to get x not equal to y and not x greater than y. X is less than or equal to y. And over here, the same postcondition. Agreed so far? And so what this just corresponds to the two weakest precondition calculations that we did earlier. Right? Because this one, to prove this, what do I have to show? If I call this Q, and I call this, let's say, P. So what do I have to show? I have to show that Q applies the weakest precondition of that code, right? This code over here, R is not X, which is P. And I also have to prove the same thing for this. So what you get is the two conjuncts that you see up on the board over there, the PWP calculation. And since both prove to be true, this at the end of the day so we're good. Okay, one last thing. Maybe you were going to go that way. What happens if over here we say R is assigned x plus 1? Being very patient. Are we going to be able to prove the postcondition?
So should I take from here? So which part should we modify in the proof? So okay, let's say we change this to x plus 1. Okay? So now let's see where we should modify. Where should we modify? Okay, this would be x plus 1. Okay? And now this would be x plus 1. Right, over here. Now, what should we modify? It seems like we're going to modify the first branch, right? Just the first one. For the first one, what should we do here? So that means we replace every occurrence of r by x plus 1. Okay, that means we got x plus 1 larger than or equal to x, and also we got x plus 1 greater than or equal to y. Okay, so now let's talk about this specifically. Okay, I'll put it here. So you got x larger than y implies x plus 1 larger than or equal to x, and also you got x plus 1 larger than or equal to y. Okay, so now what do we have? Would it be true? First of all, what about this? Is this true? Well, good. Okay, so now let's say if I know that x larger than y, right, is equivalent to this, it is actually just a simple rewriting. Okay, it will be true as well. So it seems like we can still prove it. What's wrong here? We can prove that the whole logic is correct, but the program is actually not correct. What's wrong? Which side should be blamed? Apparently, you can see this particular implementation we are giving to you, this guy here is simply wrong, right? However, when we try to formulate a whole triple, somehow we can prove that whole triple is actually true, right? So what's wrong here? Okay, good. So what's really wrong is the post condition here is necessary but not sufficient. All right? So it's not strong enough. So now, what should I put over here in addition to it? Okay. Okay. If you do that, you will see that x plus 1 over here is not going to satisfy this guy here. So you're going to make it false, right? That means you cannot prove it. That's good, because if you got something wrong, you should not be able to prove it. Yeah. Yes. So what we're doing is we're giving you some wrong implementation by having x plus 1 over here. Okay. The original precondition, the original post condition we have over here only talks about result should be larger than or equal to x, and also result should be larger than equal to y. It can be very easily achieved even without if statements. I can simply say result is assigned to x plus y, for example, right? Something like that. Okay. But now, if you simply use the original proof, like how we modify it, just using x plus 1 rather than x, and also using x plus 1 here, you can actually discharge the proof. So there's something wrong there, because we know that this change over here is incorrect. But how can the proof be discharged? The reason is the proof was only with respect to what you are given as the post condition, right? If the post condition is too weak, you're proving something that's too weak. So that's why you want to make the post condition more complete by strengthening it. Okay. Yeah. Yeah, so the more appropriate post condition that's stronger should be, we're having this extra. Is the result not only that it must be larger than equal to x and also larger than equal to y, but also result must be either x or y. You cannot just give some arbitrary number.
So basically result is equal to x or result is equal to y and result.
Yes, correct. That's the complete post condition, right? Both of them, yes. Oh, by the way, so let's say, so now we got pink and also we got green. What we did initially was only the green, and we said that it's not sufficient, right? What about we only have pink? What if we only have the pink? Would it be okay? Well, think about what that means. Okay, you can do that the proof as an exercise. Intuitively, if you only got a pink without a green, that means you don't care what the result is. Well, the result will be okay as long as it's either x or y. But what about the thing you return is actually the minimum, not the maximum, right? Yeah, you can try to do the proof by yourself. Yes.
On the next page, you said in point C that x not equal to y implies true, and it is overall true.
So you talk, okay, so this part here, this is the original precondition we have, right? You want to make sure it implies whatever weakest precondition we calculate, right? Good. So now, what's going to happen is, let's say we only got the green, let's say. Oh, sorry, let me say it again. Let's say we got both the pink and also the green. Let's say we got both, okay? We know that having this wrong implementation over here is going to make one of the branch false, right? So that means what we're going to have over here instead would be false. Okay, this apparently is not false. So it would just be equivalent to false. Right? Yeah. Or we can just give one counter example.
How do you write in the exam? For example, if you're giving us the wrong post condition, the green post condition, and then you're giving us the wrong operation, r equals to x plus y. But you say yourself that based on whole triple you can discard them and get through. How do we point out that all you understand?
Yeah, it's like a different question, right? It could be that part A, we say Okay, let's say what you're given is this. Okay, for example, right? Let's say what you're given is only the green, the original one. Okay, we say part A, try to prove the program as is it correct or not? And then part B, we can say we modify this particular branch for the implementation. And now justify whether or not this particular program is considered as correct, right? That's part B. And then when you actually can discharge it, we can ask you what's wrong. You see what I mean?
You were able to discharge it the next day.
Yeah, that's the problem, right? Because the implementation is primarily wrong, but you can still discharge the proof.
Yeah. So how do I say that the implementation is wrong?
The implementation is wrong because you
What way do I point out? Oh yeah, it's wrong.
you can say, for example, in this case, if you got max off, for example, right? If you got, let's say, 4 and 2, the wrong implementation is going to return 5, right?
Yeah.
You can say that apparently that's wrong because 5 is not the maximum of 4 and 2, so that's wrong. And then you got to justify to say the reason that we can still prove it is true was because we only got a green post condition here is too weak. So you're going to add this up.
So but the only way we can prove that the implementation is wrong by just giving a counterexample.
Yes. Everything you want to prove something that's wrong, you have to give a counterexample.
Okay, we
Yeah.
cannot just prove it like based on the whole triple or something like that.
Well, the whole triple is actually for you to prove if something is true. If you cannot prove it is true, then then original program is wrong.
No, but you prove it is discharged at the end.
Huh?
At the end you prove it's discharged.
Yes, you did. But somehow if you apply this particular implementation, you know that it's going to return the wrong result. The reason that the whole triple proved to be true is because the post condition you want to establish is too weak.
No, what
Right.
happens if it's like more complicated implementation and it's not
The same framework, basically. Every time you just go with what you're given. Whatever implementation you're given and whatever post condition you're given, you're trying to calculate what's the weakest precondition first, and then try to see if your precondition can imply that. You do that first, right? If you can discharge the proof, however, your program is going to return the wrong result. That means maybe your post condition is too weak. Okay?
Can I make a
Yeah,
comment?
go ahead.
So the problem was that it was formulated. Remember the first step? Formulate the Hoare triple. So when you formulate the Hoare triple, you have to formulate a complete post condition, not a partial post condition. And I want to show you, if you make the post condition too weak, then you can have an implementation that's wrong. If you make the post condition complete, then you do not have an implementation that is wrong. So the first step is to formulate the post condition correctly and completely. That's where the error was in this particular case. But I just want to show you a trick that's very important to know. So this example is a max. I'm not going to say max of, right? Max of x, y. Let's say they're integers. This means integer, okay? And it returns an integer. And the post condition you had over there, you had two post conditions. Right? You had the first one that said that either result equals x or result equals y, and a second post condition that says that result must be greater than or equal to x and result must be greater than or equal to y. There's a simpler way to write the post condition. That's all I'm going to show you now. So we can just say that result is equal to the following. If x is greater than or equal to y, then x else y. Now, it's a bit strange when you first look at the Greek. You should find that strange because normally when you write something like this, that after the then, you would not say a term, an expression, you would say something like a program. For example, you might write result is assigned x. That's what we did in implementation. So the point is that this is not code. This is mathematics. Okay? And what what it says, all that it says is very simple. Well, let me ask the following question. What is the type of this right-hand side of it? Is it a program, which you see in the implementation over there, or is it something else? Right, it's not a Boolean. Okay, the left-hand side, what is the type of result? No, the type of result is an integer. We're returning an integer, either x or y, right? Depending which one is bigger. So therefore, what does the type of this have to be? Also has to be an integer, right? So it's either going to return x, which is an integer, or it's going to return y, which is also an integer. So it's type correct. Okay, so this over here is an expression or a term which has type integer.
Confirm that's valid type of syntax?
Yeah.
Okay, yeah. Uh-huh. Oh, A and B versus A and then B? Short circuit. You tell me, which one? Okay, let's see this. Okay, so now if you say A and then B, let's say A and B are Boolean expressions. So basically, if you got this particular syntax, it's basically equivalent to ampersand ampersand in Java with a short circuit, which means you're going to evaluate the left-hand side. If it is true, then you bother to evaluate the right-hand side. If it is already false, you don't bother. One example could be, let's say x not equal to 0, and then let's say y divided by x is greater than 2, for example, right? You can see here it's more like a guarding condition. If this is already, actually this is actually already false, that means x is actually 0. In that case, you don't bother to evaluate this. Otherwise you got division by 0. Okay? Yeah. Another way, another one to just to have fun. The more common use for short circuit also doesn't have to be in IFO, any other language. It's by using array indexing. Okay, let's say this: a dot lower less than or equal to I, and then let's say I less than or equal to a dot upper, and then let's say a at position I larger than or equal to 3, for example. Okay? So a, let's assume a is declared as an array of integer, and I is simply an integer. Let's say read in I from some user input, let's say, doesn't matter. Okay, so now we basically got 3 Boolean conditions here. We got 1 here, we got 1 here, and also we got 1 here. Okay, 1, 2, and 3. Let's contrast. Oh, you know what? Let's. It would be better for me to do the coloring like this. Let's say orange over here, and also let's say we got blue. Okay, so now let me swap the order. Okay, let's say I got, let's say AI. Okay, now here. Let's say I less than or equal to a dot upper, and then AI larger than or equal to 3, and then a dot lower less than or equal to I. Okay, let me just make the color. So that means this guy here is blue, and this guy here is the orange. Go ahead and move that to the front. And this guy here is a green. Okay, you can see that's the only thing that changed, right? Okay, let's consider version 1 and version 2. Okay, are both versions correct? When I say correct, are we going to run into any issues at runtime for version 1 or version 2? Or we're okay? Well, we are not okay in both. What? What is that? Well, that's something you were supposed to know from 1021 or 1022, but we're going to reviewing that anyway. Okay. Okay. Anyone want to say something before I tell you, give you a little bit hints? Which one? For V2? Okay. So you're saying V1 we are okay, right? So you're claiming that for V1 under for any value for I or any value for A, we're always going to be okay. We don't ever run to any array index other bound violation. Okay. What about V2? If you claim that we might run into some array index other bound violation, what? Give me one value. 0? Okay. Because if you simply put 0 over here, let's say I is 0. Let's say A the upper is simply 5, for example, size 5. 0 less than or equal to 5 will be true. That means you will still go ahead to actually go in here and evaluate that, right? Okay, short circuit. Okay, so now back to your original questions. If you say A and just B over here, you don't have such correspondence in Java. Okay, so this is like a pure logical operator. Okay, which means you may have to evaluate both sides, even though this might be false. Okay, yeah. But if you really want to have the guarding effects for the conditions, for example, you want to make sure before I can evaluate this expression here, I want to make sure I is a valid index. You want to put and then. Okay, yeah. Okay, yes.
What if you change for these two examples?
Yeah.
Change and then to
And.
Would there be a problem?
There would be a problem, yes. If you move out then over here, then it's as if you put logically conjunction over here, right? And you know that from your logic course, if I say P and Q and R, they're simply equivalent to maybe P and R and Q, right? Because they commute. In that case, it's really up to how they implement the runtime. So they will all be evaluated. Okay, yeah. Yeah, basically the short answer is, if you want to use short circuit, it's safe to use and then. Okay, but if you want to say I don't really care which order you want to go for, then use and. Okay. Any other questions? I can leave maybe the last 10 to 15 minutes. I can just go over the proof very quickly. I'll leave the last 10 to 15 minutes. Yes.
So when we add then, we basically ensure that if previous condition has been
Yes. Yeah. Let me just summarize again. So you got basically two symmetric short circuit operator. So let's say you got Boolean 1 and then Boolean 2. Okay, and also you got Boolean 1 or else Boolean 2. Okay, in this case, in the first case, you will only evaluate B2. Evaluate it only if B1 is true. Okay, because you know that logically, if this is true, you cannot really determine the result for the conjunction. You have to see what the result is for B2, right? Okay. And for this one here is symmetric, right? Evaluate it only if what? Yep. Only if B1 is false. Because logically, you know that false or P will just give you P, right? Yeah, it comes from logic, really. Okay. Yes. Give a what?
This one is confirmed that by saying application, you mean is it the state or is it the application itself?
So you talk about state pattern. What about it?
In your device.
Which size are you talking about? You mean the one?
Almost at the end.
Okay.
Yeah, when you say application,
Mm-hmm.
is that the state or is it the application? The application.
No, actually, okay. I think I may. Let me do it this way properly. Okay, so everybody can follow. I think we're using the same example for both sections, so this one should be okay. What I will do is, give me one moment. I will just copy that particular diagram over there for the state pattern. I think that'll be easier to say. The state pattern should be here. So I should really copy this guy here. Okay, okay, that's a diagram. Okay, and then I'll go back here. Okay, good. Okay, so that's kind of the state pattern. Okay, so basically, the application over here is the clients for the state pattern. So what about supplier for the state pattern? Basically, you have the deferred state class. Okay, where most of the features are simply just deferred, except for the execute. So execute is also so-called a template method, right? Because somehow execute tells you exactly how you can combine all the deferred features together. You got similar exercise for lab number 2 or lab number 3. You should really review that part as well. Okay. So now for every of the descendant classes over here, right? Every one of them. So these are the descendant classes of the states. In that case, if you try to say, let's say for example, let's say here, okay? Let's say we declare S of type states, okay? And then here we say S.make, and now we are making the dynamic type to be seed inquiry, okay? So now when we say S.execute, okay, question for you. So which version of execute am I calling? In the state class, right? Okay, so let's modify that, let's annotate that. So the execute here really corresponds to this effective one, because we don't really find that in any of the descending classes. Okay, let's go a little bit further. Okay, so now the execute feature over here, you can look up the slide for a precise definition. Okay, it looks something like this. If I go to the execute feature over there, okay, let's say I simply got something called display. Okay, so now at the runtime, I know that the execute that's going to be called is defined over here in the state class, right? And when I try to execute the execute feature, right? Then let's say the first feature I got to execute will be display. So now, which version of the display am I going to call? In the seed inquiry, right? Because of dynamic binding. Because I know that currently S is now pointing to some seed inquiry objects dynamically. So according to dynamic binding, the display feature that is deferred in the state class over here, which means there's no version over there to be called. So you want to call exactly what the dynamic type is. In this case, there'll be a seed inquiry version. Okay, and then let's go for another one. Let's say we want to reassign S to another object of dynamic type confirmation, right? Similar, okay? So now if I call S.execute again, which version of execute am I calling? State class, right? Still here. But now if I run into the same block of code, what version of display am I calling? Confirmation, right? Because dynamic type for S has now become confirmation, right? Yeah, that's a very quick review of state pattern. Yeah, state pattern is very important. You want to know exactly how you build the polymorphic array of the states, right? The 2 lines for the descending class of observer. So observer, let's see this. So which features are you talking about? Oh, you mean this one here? Okay. If you do this one here, okay, yeah. Okay, let's say this. Right, you may want to have a look, okay, let me just copy the right thing, okay. Okay, so now what I should do is I should really copy this guy here. the short answer to your question is we want to build a bidirectional link between the subjects and also the observer. Okay, you need both lines to do that. Okay, let's see this. Okay, let me paste that to here. Okay, let's now have a quick look. So now let's say this. Let's say we have some test code. Let's say we are trying to create some weather data. Okay, so now that's how we initialize it. We got 9, 75, and 25, right? 9, 75, and also 25 over here. Okay, and then let's just talk about this particular one because all the observer will work the same way. Okay, this one here. Create CC. CC is a declare of one of the observer type, current conditions. Okay, so now let's see exactly what's going to happen. So now, first of all, you want to go to the make feature for current conditions. So current conditions over here. So the make is over here. Okay, so now the arguments we are passing is WD, right? WD is the subjects we're having here. That's a WD. Okay, so now that means this guy here is going to be WD. Okay, so that means weather data here is also a weather data is WD. Okay. That means the right-hand side should be WD, and also this this should also be a weather data. Just typo. Okay, just WD as well. So what do these two lines do individually? The first one is easy. You can see that weather data is simply just an attribute in the observer. Okay, so that means you're going to attach this weather data to that particular subjects. So what this will do is you can see for the current conditions object we have created. There's a weather data attribute over here. We want to make sure that one is assigned to this WD. That's what it does, right? And then if you go to the second one, if you say WD.attach current, attach simply means we got a list of observers for the subject. We want to attach that to as one of them. Okay? So what that would do is, what it boils down into is to say WD.observers let's say it's a linked list extend. So now think about what's current over here. What's current in this case? What's that object name specifically in the current? CC, right? Because we are creating this one, so CC is a context object, right? So now extend CC. So this is the observers list. We are extending CC to be one of them. So that means the first one is going to point to wherever CC is pointing to, bidirectional link. Yeah, it's actually very important. Okay. Yeah, don't memorize the code really. Try to understand what's really being established here by directional links.
Why would you display something?
Oh, which one? You mean the display? Over here? Oh, the reason is over here, the way I presented the observer pattern is to say the observer pattern is actually only update on demand, which means you only update the observers when the subject chooses to notify it, right? So now see the following. So now let's say this. Let's say after we have created all the observers, let's say now we decide to say WD, the subjects, to set the measurement to be 15, 60, and 30.4, okay? So that means we want to change that to be 15. 15, 60, and also 30.4. So now that means at the moment, all the observers they're out of sync because their local copy for the measure are out of sync. You want to update them. So now that's why you will see the WD, the notified. What that would do is simply, as we went through yesterday, it's going to go through all the observers in their list. And for example, the first one is going to go to this object here and call their updates. Okay? It's going to update their measures for all the data that they're concerned about. So now, question for you. So now after this, it's guaranteed this display is going to be the most up-to-date. Okay. So now, if you do cc.display over here, right? Are we required to do any updates? No, right? In the observer pattern, you only do the update for the observer when you explicitly call the notify from the subject side. If you don't have any notify in between, that means you're still using the local copy only. there's no remote communication with the subjects. Okay? So if you try to follow the slide, basically we try to say before we do observer pattern, we do a pattern where every time you want to display, you have to do some remote communication with the subjects. In that case, you might do that unnecessarily, which will waste your resources for the bandwidth. Right? Yes, you may. Yes. So the question was, could you, in your design, to say include notify as part of the set measurements? Yes, you may. Yeah, but for the illustration, we just want to put it as a separate features. Yes. Yeah. Yes. Eventually, yeah, I can do that. Maybe after some question here, I can do that. Yes. The weather data, it doesn't have to be expanded class. It doesn't have to be. Oh, I see what you mean. I see what you mean. Yes, you're right. The question was, at the moment, actually, weather data is not really on here. Okay. At the moment, the way we define the weather data class is to say class weather data, right? There's a reference type, weather data. Okay, and then something here end. Being a reference class, reference type is very important so that we can actually get aliasing, right? The fundamental difference between reference class versus expanded class is for reference class you can have aliasing, right? You can see over here, this link is pointing to the same weather data objects. And this link here is also pointing to the same weather data objects. And this link here is also pointing to the same link. They basically store the same address, the same reference. This is only possible if weather data is a reference class. But if you make it expanded, that means every one of them don't have the same copy of the weather data being observed. They might just have different copies. Mm-hmm.
Then what's the point of notify? Since it's an address, it's all pointing to the weather data file. Once it's updated, since it's just getting the address.
The problem is, if you, okay, thinking this way. So this link over here, conceptually, so this link can be arbitrarily long, well, depending on, well, thinking this way. If I say cc dot weather data, right? It's a dot notation you have to write as a programmer. But somehow, to really get to that particular weather data, to get to this object may be in the same computer, it might be distributed somewhere else geographically. So that means you only want to really invoke this particular dot notation when necessary. Okay? Conceptually, I know, because you can just put an error over here. But these two objects might be very far apart geographically. So you only want to do it on demand. Okay? You don't want to do it always. That can be quite a waste of resources. Right? You may want to review that part of the very first design for the observer lecture. Right? That's exactly why we want to move from that to the observer pattern. Okay. Make sense to you? Thinking, and then maybe look at the first part of that observer lecture. I think that's what you need. Okay. Yeah. About observer or something else? Okay, good.
So in observer, there's event design.
Yes.
And in your event design, when you have a feature change of temperature, you have event auto real. But yesterday you listed the three type if you want to pass an agent or feature object from the grid and predicate. I don't understand that part.
I don't quite understand your question here. Let's see this. Okay, for the event-driven design, okay, let's see this.
Can you go to the code where?
Yeah, that's what I'm doing. Yeah. Okay, that's the event-driven design. Okay, let's see this. Do you have a particular class you want to go over? Which class? Which one? Okay. Weather data.
Yeah.
Okay.
And then change of temperature. Event. That event is the class name for our event, right?
Event is the class that we define over here called events, which is generic. You have to instantiate the argument type. And as I said, argument type over here is for the update feature, for the update commands.
Why do we say argument arrow tuple?
As I explained before, so here tuple means your argument has to be expressed in the form of a tuple. It cannot be arbitrary arguments. So now if the update feature of yours is taking one argument, you give a tuple like this, just argument like this. If your update feature takes two arguments, in that case you would say maybe some value here and then T2 over here. Just a general mechanism of taking the arguments.
Oh, okay.
Because the update feature in general can take as many arguments as you like when they do the updates.
But we know we're just taking one argument, so if I just use arguments without tuple, is that okay?
That would be okay, but yes, we want to make your design as general as possible. In your case, that would be too specific to the particular application. You want to make it as general as possible. Yeah. Well, of course, it depends, right? In the exam, if we want you to program the way that we as general as possible, we might just give you this, right? If we want you to program from scratch the events, in that case, you may get rid of this if that's not necessary. It's up to your judgment, really. But I'm just trying to say this is the most general way of doing things. You want to say the arguments you want to pass to the any update command will be just a tuple. It could be the tuple can just be empty. Let's say the update doesn't take any arguments, right? It could be that the update takes one argument, or it can be it takes two, or it can be taking three, etc. Okay. So you want me to review event-driven design, which part, or the whole thing? All right. Okay, I'll give it a try first, and then you can tell me if that's enough. Okay. Basically, the way event-driven design works is very similar to observer pattern. Similar. Okay. Basically, you want to make sure the observer is somehow attached to something, and also the subject also maintains certain a list of things over here. You know what? Let me show a diagram quickly. Okay, this would be a nice diagram, but I'm gonna just copy that here. Okay, let me say before this, I'm going to just show a diagram quickly. Okay, so that's the idea about event-driven design, right? So now, basically, you can think about, you can have a many-to-many relationship. So you can have multiple subjects, like a multiple metadata. And also you got multiple observer, like a multiple apps over here. That's a general many-to-many operation relationship. Okay. So let's say every event simply just corresponds to a certain measurements for the weather data. So it can be temperature, for example, right? And now, every time if you got any updates on the weather data, specifically you got any updates on the temperature, you can publish to this particular event because you know there's a change on the temperature. And at the same time, you want to make sure that particular event is also subscribed by all the relevant apps over here. For example, for the case of temperature, the current conditions should get subscribed to it, right? On the other hand, if you talk about the forecast, the forecast app only cares about pressure. In that case, you don't have to be subscribed to this particular event. So it's much finer grained for subscription and also publication. That's the big idea about event-driven design. Any question about this part? Okay. Yeah, if you really want to review the whole story about event-driven design, how we go from observer to event-driven design, feel free to refer to lecture recording. Okay, that'll be the best way. But let me just say one more. Okay. Actually, you know what? You got a question about this diagram here? Yeah, exactly. So now, in the case of the weather data example, I'm just showing one event. Of course, you should have another event, just call that change on, let's say, humidity, right? There will also be events. In that case, you will be subscribed and also published by different, subjects and observers. It's actually much more organized way to actually to manage the many-to-many relations. Yeah. You mean the event? They're different classes, actually. So you're talking about implementation. Okay, I assume that you're okay with this diagram here. Let's go ahead and look at the code very quickly. Okay. First of all, you have the event class over here, right? the event class over here, as I said, to make it general, argument should just be a tuple. Okay? And then over here, you can see in the case of the observer, you have the subject class which maintain a list of observers. It's not the case in the event-driven design. What you maintain is simply a list of procedure, right? So that means we're using agent function to store pointers to the update functions, to update procedures, okay, rather than observer objects, okay? And then you can subscribe, you can also publish, okay? So let's see exactly how you subscribe and publish, okay? If you go to, let's talk about subscription first. So this is one example for the observer. How do you subscribe an observer to some events? This is how you do it. So when you first create the observer over here, okay, what you will do is you want to see, let's say, current conditions only depend on temperature. In that case, I only have to subscribe to the temperature and humidity. Again, it's a typo. Okay, change on humidity and change on temperature. Only two events have to be subscribed for this particular app. Okay, and now when you subscribe, okay, now you can see we're using agent over here, right? So now, what does that really mean when you subscribe? What are we passing over here? At a pointer to the update procedure, right? You can see, for example, update temperature and also update humidity. Notice one thing here. If you look at update temperature and update humidity, it takes exactly one arguments over here, right? Okay? So now, let me link a little bit to the agent example we talked about before. Yeah, I'll get to you. Yeah, one moment. If you actually put something over here, it's as if you say agents updates humidity, and then I'll leave that particular real number just open arguments, which means it's going to be filled in later, right? That's what we said before. Yeah, go ahead.
So we don't have to put the question.
You don't have to. If there's only one question mark, you don't have to.
But if there's two,
You have to, you know what? Let me say that again. If you want to leave every argument open, you don't have to put any question mark, okay? So having this over here is as if I say it's going to be question mark for every argument you have. However, sometimes you might have something that I'll give, let's say, you might want to say agents over here, I have some update feature over here. The first one should be open, the second one should be 23, the third one should be open, and the fourth one should be something, right? In that case, you want to be specific, yes. Okay. Okay, that's about subscription. Okay, and then if you go to the subjects, which is weather data, right? It's going to publish. How do we publish? Basically, we know that in the specific events, we store the list of pointers to the update functions. So now it's time to call them. So what you will do is you will simply just go to okay, over here. You can see the set measurements. You actually go back to your original question. Can we include notify in the set measurements? That's what we do in the event-driven design. Okay. So now you can see that when I want to set a measurement to be some new temperature, new pressure, and new humidity, I can say, for example, let's say change on temperature, that's an event. And then I will simply say publish, right? So what do I need to publish? Well, I want to publish a new temperature over here, but it's a tuple. So now the tuple here corresponds to the tuple over here. Okay? Guys, make sense? Well, since the code is available to you, right, you should really try to download the code and try to play with the example a little bit, right? It's not a very easy to understand intuitive architecture. That's why you want to play with the code a little bit so that you can answer the exam questions. Yes? Yes, just one event. And the event class can be instantiated to different events. Yeah. About what? The what, sorry? Yesterday. It's different. Okay, so agent itself is easy. Agent simply give you the pointer to some function or command. Okay? But now, you can think about event-driven design. We're trying to show you one possible application of agents, which means you store the pointer to the update procedures into the events. and then you can publish that later. Okay, that's one application. And when we talk about counting quantifier, it's just like a second application, which means I want to just go over an array and then apply certain Boolean function to every element in the array. How do I do that? I can actually store that function there in the counting procedure, right? These are different applications.
Yes. So I just want to ask for the counting rate. So you actually put a function at there. So this is the type, right? I want to know which one you go first. What's the order?
Okay, so let me just go back to what we said yesterday. That might be easier. I'm talking about the, okay, that's the original counting, okay? What about, can you repeat your question again?
Okay, so where you result involves counting.a, then something like that.
Yes.
So what's order? Is that, I know it's going to count first, and then you
Okay,
function,
okay.
which is a function, or it's going to the
Okay, let's see this. Okay, result, okay, I'm talking about, you count this line here, right? Let me write it down. Result is assigned to u.counting A, okay, and then agents over here, and then u dot is positive. And over here, you can either say question mark over here, or you can leave it out. Okay, either way. Okay, let's say we do this way here. So now you talk about order of evaluation, right? Okay, good. So now, before you can actually, here goes like a general mechanism for any programming constructs. If I want to evaluate this particular method or feature call, I want to make sure all the arguments are ready, right? The first argument is simply referring to the reference to some array. That one is ready, okay? And now, the second argument over here is going to be agents, which means I'm going to get the address of certain feature. In this case, is positive feature. Get a reference for that, and then I'll leave the first arguments, the only argument just open, which means when I store this reference here, I don't commit to any of the arguments yet. Okay? Okay, so number one, number two. Number one, number two doesn't do anything. It simply just makes sure the arguments are there, so you can call them, right? Okay. Number three is when you try to call this counting over here. So what's going to happen when you call? Well, you simply execute the body of the counting, which is going to be a cross loop. So when you go for the across loop, you're going to go for element by elements, right? And for each element there, you're simply just going to, when you say cursor the item over here, you're simply going to give this element here, and then, okay, let's say this. So now when you do counting over here, right? Okay. Okay, let's see this. Counting, and then you will say do and end across AS cursor and then loop. And then you will say something like if f cursor the item over here, and then you do something over here, right? That's the implementation, okay? Let's say for the very first element over here, cursor the item is going to be 1. Agree? Okay? So that means cursor the item is just going to be 1. So that means you're going to call whatever, you're going to invoke whatever function we just store with the argument 1 for the first iteration, right? And that one is going to make sure we're going to pass 1 to is positive. In that case, it will be positive, so that's simply just true, right? For the second iteration, we're going to get to the second element here. In that case, it's going to be 2, right? Just so on. Yeah, the idea about it is simply you abstract away the loops, right? When you say agents, basically you can think about, again, look at this expression over here. You are counting A and agents, this one here. If you look at this particular orange expression here, there's no loop explicitly. However, under the hood, there is a loop. So we're abstracting away the loops using the agent function, basically. Yeah, you just basically you want to say you want to go over the array in a particular way. Okay? Okay. Okay? Good. Yes. Okay. I have. You know how to look for that? Actually, the number of views is not that many so far. I'll show you where to get it. You can, first of all, go to my lectures page. Okay, go to my web page. You'll see under lectures, 3311. Okay, and I think the last entry in the table over there. Okay, the recording over there. Okay, you can go for there. Yeah. Huh?
For
The previous slides. Yeah.
here, Sean, can we get rid of the question mark for the without exposure?
Yes, you can. If you want all the argument to be open, you may ignore that. That's fine. Its syntax can support it. However, if you want to be flexible, to say maybe the first argument should be open, but the second argument shouldn't be open, then you should not just leave it out, right?
Why in our class for the data where there's a the teacher change of temperature, we don't have like f dot function like that, like the one that you're doing in config?
So there are different ways you can call that. So you're basically asking about, let's say this. Let's go back to the code over there. It has different ways of calling the function that's delayed. Let me just go back there. Okay, you're basically talking about this guy here. Let me just find it out. Yeah. Okay, basically talking about this. Okay, so you can see actions over here is simply a list of procedure. So actions, the item over here is simply just procedure. The old way of doing things before the current syntax you're using, you're gonna explicitly say call, and then the arguments, right? However, the one I show you in the agent is alternative syntax that's newer. You can also say actions, the item, and then you can simply say arguments. That will also be fine. So this will be closer to what I show in the counting quantifier example, right? So you don't have to explicitly say call.
What is the change in temperature on the website?
Where?
You don't have like argument.
So here, what's different, right? If you say publish, you have to give the argument over here as a tuple. It's a different thing. So you're over here, when you say publish, you're not really calling the function just yet. You're just passing this particular argument here.
But change of temperature is not in the future change of temperature. You're taking arguments from given by the current condition class.
I don't quite follow your questions.
If you see in current condition class,
Current conditions?
yeah, current condition class, you say w.change of temperature subscribe agent, right? So that's an argument, just feature argument.
No, you are confused. Over here, if you look at subscribe over here, subscribe is expecting some procedure. That's why we're passing a procedure. And the way you get a procedure is by using agents. Yeah, you really want to look at all the classes that's involved carefully. I think you are not still very confused about the architecture over here. Okay, yeah. About what? The exercise. We're going to do it. Okay, how about we do it? If no other question, I will spend about 5 to 10 minutes going through last part of the proof quickly. Should we do that? Okay. No other questions? Okay, good. Let's do that quickly. So basically, you can find the exercise on the web, right? If you go to, again, my web page, over there, you can see the exercise over here, okay? You know what? I don't want to really go exactly into details for the proof. It's going to take 1 hour. You don't want to stay for another hour, okay? Just 5 minutes, okay? I'll give you exactly what you should know, okay, quickly. The exercise basically gives you this particular feature called find max. Similar to max off that we talked about in the class. Rather than 2 integers, we've got an array of integers, okay? So you're given this fragment of code, okay? The question is this program correct or not? You follow exactly the 3 steps, right? You asked me about. That's exactly the proof you want to do, okay? So now if you look at the exercise solution there, so your task would be to prove or disapprove the program is correct or not, right? And there are 2 things you want to prove about loops. One is about partial correctness, and the other thing is about termination, okay? 2 things. Okay, so now you got to do formulation, which I already show you in the next page. I'll show you quickly. And also you want to prove or disapprove. So now if you go to the next page, these are all the formulations, right? Very easy. You can see over here, let's say you want to formulate, I can establish looping variance. I simply copy and paste, first of all, the precondition there. Okay, and also I got the looping variance over here. So that's looping variance. And also this is the from part, right, for the loop. You can formulate very easily, okay? So what I included in the final page is the most difficult one. How do you prove the maintenance of the invariance? Okay, what you have to prove is like this. This part here is not the case of the exit condition. And this part here, this long part here, is just about the looping variance. Okay, we want to make sure looping variance is still true. Okay, and inside is simply the body of the loop. Okay, overall that's what you have to do. Well, that was answered yesterday, right? What's that? Anybody? In case of? Anybody want to help? What's vertical bar? Such that, right? Okay, and it is the case. Okay. Oh, by the way, so okay, it's good that you mentioned. In my case, I simply use a dot. I believe in Jonathan's section, you might just use a colon, right? Okay, colon just dot. Okay. So in the exam, well, you can feel free to put this notation in your data sheets, right? So here, either put a dot or you put a colon. They mean the same thing. Okay, both are correct. Okay, just a notation, right? Okay, so now what you will see in the next page basically is how we prove it. Okay, I'll just give you the big picture quickly, and I'll highlight the critical theorem you have to know. Okay, so now if I want to prove this particular whole triple is correct, it's true, what should I do? 2 steps. What are the 2 steps I got to do? Find the WP, and then to make sure the original precondition implies WP, right? Good. Okay. So now what you will see over there in the next page would be, okay, so first of all, calculate the WP. Okay, for calculating the WP, there's only one thing I want to highlight, okay? Every time, if you have, so this is the body of the loop, okay, that's the body of the loop. And then this guy here is basically loop invariance. However, something I want to make sure, which I also mentioned in the slides, every time if the part of the post condition also has some array indexing over here, you want to make sure the index is actually valid. That's why you have to augment your post condition by this particular conjunction. That's something added. Okay, something to make sure. Okay, that's the only thing I want to say when you calculate WP. So which means in the exam, if the WP you're trying to calculate involves some array indexing, you want to strengthen the post condition by saying the array index should be valid. Okay? So now, WP part is actually not too bad. Okay, you can definitely do the exercise and make sure you got something like this. Okay, eventually. Well, because we got a if then else, so that means you got either B or not B, right? And also conjunction. Okay, so now what we want to do is to say the original Q, the precondition, implies this guy here, right? So if you want to prove that Q implies, let's say P, let me say this, P and R. Okay, you can do it separately. Q implies P, and Q implies R. Okay, you can do them separately. Okay, so now what I showed you here is just one of them. You can do the other one as an exercise. Okay, so now let's see this. So now if you look at this big thing we are trying to prove over here. So now let's say this. So this guy here, this whole thing, the orange part, this guy here is exactly the first conjunction we are having. Okay? Right? That's exactly the P that we talk about. Okay? You want to make sure this is, if you look at the this is the not exit condition, and this part here is the looping variance. That's what we want to prove. Okay? I want to just say something quickly. You will find that to discharge this particular proof obligation, it would be very useful to use, it's called split the range theorems. Okay? Let me just read it out to you, and I'll give you one example. It's very straightforward. You'll say for every j such that a the lower and also I, right? And also you say pj. Okay? Can you actually look at that and tell me that makes sense to you? I'll give you one example. That might be easier. Have a look at that, the yellow part. Does it make sense to you? Okay, I'll give you one example. If I say for every j such that 1 less than or equal to j and less than or equal to, let's say 10, it is the case that, let's say, is positive j. Would this be true or false? True, right? I'm asking if every number in the range between 1 and 10 is actually positive, right? To do this, it would be equivalent to, I can say, okay, think it this way. I'm basically talking about between 1 and 10. What I could have done would be, why don't I simply separate between two regions? One is from 1 to 9, the other one is from 9 to 10. That's the idea, okay? So what I would do is, for every j such that, so now I'm going to split it into two parts, from 1 to 9 and also 10. So 1 less than or equal to j, less than or equal to 9. Okay, that's why you see I minus 1 versus I over here. Okay, and then you say is positive j. And so now what's left out? 10, right? Because 10, you can say it's 10 versus 9. So now over here I can say and is positive 10. Okay, that's really the, you can see 9 and 10, and then between 1 and 10. Okay, you can think about these two ranges are really the same, right? Versus if you got this guy here, and also I minus this one here, and also I. You're just talking about same range, right? You just split the range into two parts. Yes?
What's the dot equivalent? I think the dot that is 5 and can you
You need a dot over here?
yeah, I mean the dot, what's the equivalent?
Well, you tell me. If I say for every x such that some range, and also it is the case, some predicates. So what's that equivalent to? Implies, right? Which means you only worry about the result if the range is in the range. If it's not in the range, you don't care, right? On the other hand, if you change this to exists, what would that be, right? Okay, yeah, we have no time to explain exactly why, but you can, if you don't feel comfortable about it, put it on your data sheets. Okay, let me say one more thing before I answer your questions, okay? So that's the split the range you have to use. Okay, so now what you have to do when you go for the proof, this will be the most critical step over here. So now what you want to do is over here. You want to somehow get this particular predicates, and also you want to get this predicate as well. Okay, these two. Okay, you can read the proof for detail. Okay, so now if I combine this and also this together, okay, so let me write it down. AI larger than result, and I also get result larger than or equal to AI. What does that mean? Well, it's almost like a transitivity, right? If you say A larger than B and B larger than or equal to C, right? What does that imply? AI larger than or equal to AI. Make sense to you? Yeah, that's like a trick for this particular example. If we give you something different, you got to work out, the tricks for that particular one. Okay. So the main lesson from this, of course, you don't really memorize exactly this trick. My point is, during the exam, when you want to prove something, you want to really look at the predicate and see the reason I could do this was because think about the big picture. I'm really trying to prove this particular looping variance over here. But in order to prove it, what kind of assumption can I make? So this is the branching condition over there, either one branch, right? And this is the case, not the exit condition is true, and also the looping variance is also true in the beginning. So these are the three things, 1, 2, and 3. Somehow you want to work out, in order to prove this one here, how can I use 1, 2, and 3 to prove it? Guys, do you see what I mean? Should I repeat? Okay, let me repeat once more, okay, quickly. Okay. The picture is you want to prove not B and looping variance I implies. Okay. And also you got, okay, that's an exit condition. Okay. Okay, and also not C. Okay, this is the branching condition. Condition 4. And then you will say implies the looping variance. What we want to prove eventually is really just the looping variance, right? But in order to prove it, we can assume different things. Which means you can take it for granted. You want to say, in order for me to prove this, I can use something from here. I can use something from here. I can also use something from here. That's basically what the proof is trying to do. Make sense? Yeah. I wish we could have more time, but yeah. But for this proof, just try to learn exactly the structure, right? Yeah. The exam may not be as hard. It will be no harder than this. How about that? No harder than this. Huh? Oh, split range is only specific to this example. I would say whatever we expect you to do, it should be very common theory. You should know. Yeah, you don't have to worry too much. Split range, you know what? To be safe, you better put it in data sheets, right? Yeah. Okay, how about we have a few more minutes? Okay, running over time, right? Yeah.
Yeah, just one more. So running here, it's a loop, and inside the loop is a cross R, right? So what happens is you have a cross R to use two loops. I mean, inside the loop.
You mean you have nested loop?
Yeah, the nested loop.
I would say don't worry about nested loop. That'll be too complicated. Yep. You may be right. Yeah. Yeah, could be. Yeah, should be greater than. Actually, you know what? I may have copied some variable wrong. But anyway, so, oh, it's AJ. Sorry about that. You're right. All right, there we go. Yes, good. All right. Okay, guys, any more questions? Okay, yes. You can type as well. Yeah. All right, best of luck for tomorrow.